So thank you very much. Many thanks for the organizers for inviting me, and it's a great pleasure and honor to be here to celebrate Jean-Pierre's work. So I have to admit, I do not belong to this beautiful and big family, academic family of Jean-Pierre, but I visited Grenoble several times in the last 15 years, and so this place holds a very special place in my work and heart. So I came several times for the algebraic and Kähler geometry workshop series, actually, which Jean-Pierre organized. Last time I was here in 2020, and it was a bit memorable because that was the week when the start of the lockdown in Europe for the pandemic lockdown. So it happened here, actually. So some of you probably remember we had a really nice excursion to the valley on Tuesday, and on Wednesday morning, actually, suddenly, Europe and everything has changed. So that was in 2020. So it's really great to be back here. And so the plan for today is really to it's going to be a survey talk. So I would like to show you some research development regarding the geometry of jet bundles, but also in the second half, I will actually really focus on hyperbolicity and Jean-Pierre's work. So that's the plan. So kind of the goal today is give you a motivation or justification why, for a complex manifold X, you can think of also as a non-singular projective variety. Why jets of holomorphic maps from C to this complex manifold play a crucial role in many enumerative geometry, algebraic geometry, enumerative geometry problems, and also in complex geometry. So in the first half of the talk, I will really mainly focus on algebraic geometry and enumerative geometry problems. And then in the second half, I will turn on complex geometry and hyperbolicity. So let me start with it's kind of a very, very simple basic object, right? It's really easy to define, really easy to write down, and still it's a really surprising and amazing thing how much information this moduli space actually stores. So that's kind of the idea. So let's start with this vector space. If I press, yeah, that's the light. Yeah, okay, sure. So this JK1n, this is the jet vector space of jets. So jets of maps from C to Cn, which sends the origin to the origin. So it's really just a k-tuple of polynomials which are the derivatives of this function. So we are only interested in the k-jet, so it's a finite dimensional vector space. So in other words, this is just a vector space of dimension k times n, right? So what makes it interesting is that there is one thing, well, many other things as well, but there is a group action on this space. So you see, which I denoted by JK reg11, which actually just following this notation is the set of maps or jets from k-jets from C to C, because it's 1, 1 now. So you know, if you take a phi, which is a map from C to C, preserving the origin, then you can use this phi to reparameterize your map from C to Cn, right? So that's a natural thing. So it will not change the image of this map, but it certainly is a sort of symmetry of this object. If you look at the maps from C to Cn, we would like to see these as modulo this reparameterization group. So it's a composition. So let me put down this in local coordinates. So we pick some F is a map from C to Cn, so it's like high school mathematics now. It's a C to Cn, right? So we take a F, which is just this Taylor expansion of 2 degree k. So you take the first k terms in the expansion. That actually gives you this element in JK1n. So these are the coefficients, F prime, F double prime, F to the k, so the first k derivatives. And now we take another map, which is just a map from C to C, phi is again it's just a simple polynomial in one variable z of degree k, right? Now the only issue is that if we want this to be in this group, then we would like to ask alpha 1 to be non-zero, so that it has a formal inverse, and then it has an inverse in this group, because when I say like it's a group, it means that jets with non-zero linear terms can be inverted, and then take the jet of that inverse. So that's kind of the group structure. So if you put down it's just a composition, you put phi into f. So we put phi z into z. This is what you get. So it's basically a matrix, it's a linear action actually. And it's given by this linear group in GLK, which has this really nice upper triangular form. So we have alpha I powers of alpha 1 in the diagonal. It's upper triangular. And you see it's generated of parametrized along the first row. So I have the parameters alpha 1, alpha 2, alpha k in the first row, and all the other entries are some sort of polynomial entries in these alpha i's. But this is actually a group. And then, so this is not reductive, but it's actually a semi-direct product of a C star, which is the diagonal C star. So when alpha 2, alpha 3, alpha k is equal to 0. And this unipotent radical UK, which is when alpha 1 equals 1. So you make alpha 1 to be 1. That's a unipotent subgroup, and then this is just a semi-direct product of these two. So it's very importantly, this unipotent radical is a normal subgroup in this group. So this is what we call, later we call this a C star extension of a unipotent group. Or in other words, this group is a graded group, which means that it has a central C star, which such that the action, so you know, if you take the C star action on the Lie algebra of the unipotent, or the Lie algebra of the unipotent radical, it has positive weights. That's what I will actually use, really. This is due to the fact that these powers of alpha 1 are increasing along the diagonal. This means that if you take the action of C star on the Lie algebra of U, this end-joint action has positive weights on that. And that's a crucial fact. This is what we will actually use. This is what kind of the pretty mild but important assumption about what we call this non-reductive geometric invariant theory. So this is the setup. So this is a very, very simple object. Like a vector space, you can take the regular part of these jets. Actually, then it's like an open subset of the affine space. But we have an affine space, a nice algebraic group acting on that. It's a linear action. The group is not nice, but still seems to be very simple. So now, from now on, I just call this the moduli of K. So the quotient now, which is kind of the jets modulo of reparametrizations, that's what I call the moduli of K jets, or jet moduli space of order K. So yeah. So this is actually an object which plays a crucial role in several, a central role in several geometric problems for obvious reasons, but it's kind of, I would just really want to justify this. So there is a fibered version of this. Is what we call the jet bundle. So imagine that now you have this X complex manifold, and we take we take a curve written in some local coordinates at T on C, and some local coordinates on X. So then the K-jet bundle is really, what is the K-jet bundle? As a set, is just the set of jets of maps from C to X. So we just take any kind of, take local coordinates. You can write it down in local coordinates. And such that, you know, this is a fibration over X. The fibration map actually sends this jet, you know, to its value at the origin. So that's what we call the jet bundle. And this jet bundle is you know, the first thing we realize, this is actually not a vector bundle. So the structure, it's actually a fiber bundle, but its structure group is not linear. It's actually not a vector bundle. It's an associated bundle to the universal diff X bundle, which I denote by diff X. What is this diff X? This is the universal diff Kn bundle. It's kind of diff kn is the set of local reparameterizations of Cn, right? So X has dimension n. You take the group of local polynomial reparameterizations of Cn, that's a group. You take the universal bundle, and then you associate to it this vector space. And that's what we eat. That's what it is. Like if you want to do a topological definition of this bundle. So you see that the structure group is not linear. It's kind of this other big non-reductive group, and that's kind of the fiber version of this jet moduli space which I talked about. Now, one thing is that if you have at least a jet from C to in X, so jet of curve, then it's actually can lift it to the jet bundle for any k. And the other thing is that this jkx has a fiber-wise action of diff k, so these reparameterizations of the group of C, right? So if you have a germ of a curve in X, you can reparameterize this C that actually commutes with this diff kn action. So there's an induced action on this bundle, which is a fiber-wise action. So the fibers of this, I mean, the point is that the fibers of this bundle are really this quotient which I defined here. These are these jk1 and mod diff k. This is the moduli of k jets, right? Those are the fibers. Now, so the key point here is that I really like to make this point here. So kind of this is a survey talk. So I would like to just really give you an idea why this quotient is important. So this is a moduli of the jets on Cn, jets of curves on Cn. So the point is that this is a quasi-affine variety, so it's not closed. So we talk about this as a quotient, as like a set of orbits, right? But so they are, you can define different completions or compactifications of this moduli space, and that's there are different compactifications which actually turn out to play central role in different problems in geometry. So they go in different directions. So the first thing is, let's say this on the left-hand side is this curvinar Hilbert scheme. This is a component of the Hilbert scheme of points on Cn. This is C Hilb k plus 1 points on Cn. The 0 means it's supported at the origin. So those are those ideals where the quotient is isomorphic to this Morin algebra. That's this locally. These are fat points which come along a smooth jet of curve. Now this is a singular projective completion, but the point is that this is endowed as the Hilbert scheme of points actually plays a really important role in enumerative geometry and physics. This actually endowed with a tautological bundle, and that's the reason why this is very important. There is a tautological bundle which is really just this quotient as a vector space. So tautological intersection theory includes enumerative geometry problems. So here is some of them which I quickly go through in a second. So they are important in curve counting, Thom polynomials, multi-singularity classes, and Segre integrals, Segre-Verlin, the duality question. So kind of it's an important object. Now there is a second compactification or projective completion. This is actually what we call now the non-reductive GIT quotient. It's a non-reductive group, so this I will explain roughly, like very quickly, how this actually works. It gives you a non-singular projective variety. And the nice thing about that this is a canonical in the sense that there is a nice intersection theory of this quotient. And as we will see, the main theme of this talk is really cohomological intersection theory of this jet moduli space. So we are really interested in intersection theory of this space. And the point that this non-reductive GIT quotient has a nice intersection theory in the sense that the Jeffrey-Curven type integral formula which is very well behaves. That's the point. And that helps actually in this application in hyperbolicity, which gives this polynomial bound in the hyperbolicity conjecture, which I also talk about in the second half. The third compactification, which was kind of, these are rather kind of independently was constructed, but this the first one actually historically was this what we call now the Demai sampler bundle. This is a iterated tower of projective bundles. So I will not explain the construction, but this is again a non-singular projective completion. This is traditionally and for decades it was used for in hyperbolicity questions in a very efficient way. And in particular for these Green-Griffiths, Lang, and Kobayashi hyperbolicity conjectures, it turns out it gives you slightly less efficient, like an exponential or double exponential bound for the degree in these conjectures. It somehow comes from the fact that this is really a tower, and kind of our understanding is getting we're getting more and more into the point why this is actually less efficient for this problem rather than using this other model. Anyway, so these are the three compactifications, which, and there are I guess there are many others, but these are very important compactifications. And so now in the next 15 minutes, I will really focus a little bit on applications in normative geometry, just to advertise these problems as well. So let me start with this. What is this Hilbert scheme of points, and what is the curvinal Hilbert scheme? So I guess everybody knows this, but let's go through this. So the Hilbert scheme of k points on Cn is really the set of ideals in this polynomial ring in n variables of colang's k. So the algebra R mod I has dimension k over C as a vector space. Now, so there is a punctual part of this Hilbert scheme, which I denote by 0 down here, is the set of those ideals where this algebra is supported at the origin, right? So these are really so how do you think about Hilbert scheme of points on Cn? It's kind of a moduli of k points sitting on Cn, and we compactify it. So the question is, what happens when these points come together and form? And this is kind of the deepest stratum where all points come together, so when it's kind of a fat point, right? And they all come together at the origin, right? Now, there is the problem with this Hilbert scheme of points on surfaces is it's a non-singular nice 2n-dimensional manifold, and it's really occupies the central place in physics and mathematics. But on three-fourths and higher dimensions, when n is at least 3, this is not irreducible anymore. So we have many components, and the geometry is really pathological. So but there is this distinguished component, which is what I denote by G Hilb k Cn. This is the closure of the locus where the points are all different, right? So you have k different points on Cn, and then the question is how they can collide, what they form when they collide. And then it's actually an irreducible component of the Hilbert scheme. Then the intersection of these two is kind of the punctual geometric component. So these are supported at the origin, but they have a deformation into k different points. And that part actually is still not irreducible. It has a distinguished component, and this is really an irreducible component. This is this curvinal Hilbert scheme. So these algebras actually those which deform to a smooth curve, right? And it's highly non-trivial which points belong to this. You have to take the closure. So it's a highly non-trivial deformation theory question, which points on this Hilbert scheme, so which subschemes of length k deform into a smooth curve. So let me just summarize quickly this picture. So on surfaces everything is nice. So these two things are the same. So the Hilbert scheme is irreducible, and these two are the same. The punctual Hilbert scheme is irreducible. These three actually are the same. The punctual Hilbert scheme is irreducible. Due to Biancon, it was his thesis actually. It's a singular, this punctual Hilbert scheme is irreducible, singular, and moreover, it's a complete intersection in the sense of Hyman it's a tautological complete intersection, I would say. For when on free folds and in higher dimensions, we have a very pathological behavior, many components. We don't understand the geometry. We don't know really the deformation theory, but they become more and more important in the recent years. So here is a picture which I really like to show. This is what I call the Bérczi. This is actually appeared first in Joachim Jelizsiev's thesis. It summarizes these geometries really nicely. So this is really a flower. So what happens here is the following. So you have the stem, which is really this. So all the stem and the petals are components of the Hilbert scheme, and the stem is the main component. So that's this geometric component where the closure of the locus where the points are different. So you can see that the ladybirds have different, like 7 different dots. So that's in a generic point, and that's the main component. Now, this singular dimension k times n. So the petals, these are all the other components of the Hilbert scheme. And then there are some 2 colors here, the yellow petals and the red ones. So the yellow petals are punctual components, which means that on these components, these are components of the Hilbert scheme, but generically there's a big fat point. So all the points collide to 1. And you see that the punctual component also has a component inside, on the boundary of the main component as well. So, and then there is this distinguished yellow petal. This is this distinguished component of the punctual Hilbert scheme. It's conjecturally the smallest one. Still, surprisingly, and this is really I think it's a very surprising recent development, this kind of, at least it's a surprising fact, that this very small component contains all fixed points, torus fixed points of the Hilbert scheme. In other words, all monomial ideals sit in this component. In other words, every monomial ideal can be deformed to a smooth curve. This is kind of a highly non-trivial fact. So even if you start to like playing with this, and I can give you like types of monomial ideals, in other words, high-dimensional Young tableau or partitions, where this I still can't construct this deformation by hand. So I don't know the deformation, but we can prove that actually such a deformation exists. It's a highly non-trivial fact. But it's also very important, which I will not talk about today. It really has important implications in intersection theory. It somehow induces somehow that not just this, but it's actually is part of this story, is that integration on the main component can be reduced to this component, to this curvilinear Hilbert scheme, and this curvilinear Hilbert scheme is actually a non-reductive quotient, so you can apply some other techniques. So it has really important implications for intersection theory. Okay, so so why this is a nice compactification of this jet moduli space? Why this is a distinguished compactification? Because there is this tautological intersection theory. So tautological bundles exist over this compactification. So for any bundle V over your X, it's a rank R bundle. There is a tautological rank RK bundle on the Hilbert scheme of K points of X. Was is the the fiber over a subscheme is really just as a space of sections. You can define in that way if you want. It's really a tautological bundle, and the tautological integrals. You take any symmetric polynomial, so you take any intersection number of this bundle. It's kind of what we call tautological integral. Now the question is how and where can we take this integral? Well, the point is that you can. This is now an ordinary bundle, and we can take ordinary intersection numbers over some irreducible components. So over the main component, it makes sense to integrate. We don't really understand. Let me tell you. So you either focus on this main component, which is enough for many animative geometric problems, or there is another direction where you can do virtual integration and virtual intersection theory, where you focus on the full Hilbert scheme. But then the problem with that is that it's quite limited. So it's not clear how to define these virtual classes or on 4 folds and higher. 3 folds, they work nice. But actually, if you really want to take actual intersection numbers, this is enough in many sense, as I will indicate. So taking this integral over the geometric subset, or this main component. More generally, we can take geometric subsets. So what you take is you take a set of algebras, finite dimensional quotient algebras, and the dimension of the ith is ki, and they add up to k. And then we define this Hilb A1 up to ASC. It's kind of, this should be an AN, so CN, sorry. So we take, what happens is that you take S different points, the number of algebras. At each point you put an algebra, so you specify the type of your subscheme at that point. This is going to be AI. You take S different points, you specify the algebras, and then that's a subset of the Hilbert scheme of K points, and you take the closure. And of course, the question is what happens in the closure when these deform. It's getting very complicated. But the fact, here are examples. So if you do the Hilbert scheme of K points on Cn is really just the main component. The main component is really just where you take the trivial algebras. And the curve in a Hilbert scheme is when you take one algebra, AK, which is this Morin type. So, and there's this theorem of Jörn Rennemo from 13 from his thesis, which says that kind of this fits into a long list of similar results, but it says that there's a universal formula for these integrals. So if you take this intersection number, this is given by a universal polynomial depending only on A1 up to AS, such that if you substitute in this polynomial the Chern numbers of the bundle, the original bundle, and the complex manifold, it gives you this integral, right? So the right-hand side really depends on the numbers of x and v. The left-hand side that's actually what we want as a tautological integral. The problem is that the techniques for this proof, there are more than one proofs now. They are kind of use this algebraic cobordism theory, some of them. So it's kind of very general, but they never give you concrete formulae. So, and that's actually what happened. This is where I wanted to get here, is like there are some recent developments in this direction. We can have iterated residue formula for, so there's this, using some sort of geometry of this and some sort of equivariant techniques, we can actually come up with formulae for tautological integrals, first for the curve in a Hilbert scheme. Then we can also reduce tautological integrals on the main component to the curve in the Hilbert scheme, and then come up with some formula with that. So that's roughly this. But let me mention a few applications. So this slide is about the applications. So what sort of animated geometry applications we have for these tautological integrals? Why they are important in some sense? And that's actually goes back to the first application. It goes back to the 1950s and René Thom. This is about singularity locus of maps. So we take again a map, a holomorphic map between two complex manifolds, N and M, and with positive codimension. So the dimension of N is less than equal than the dimension of M. And when we take this algebra AK, but you can fix your favorite finite dimensional algebra if you want. Now we take this, that's what I call the Morin algebra. So the Morin singularity locus is sigma kf, is those points in the source space N where this f has local algebra isomorphic to AK. So this type of the singularity of f at the point is given by this algebra AK. Right? So that's the crucial thing. You can classify. We have a generic map from between two complex manifolds. We can classify the source space with respect to the local algebra of the map, and that's kind of the story. This is what René Thom started in the 1950s. So in particular, he proved that if f is sufficiently generic, that then this AK locus of the map is really an analytic subret, and it gives you, in particular, gives you a cohomology class. So there is and that's actually also polynomial in it has a special form. It's a polynomial in the difference bundle of n and m. So what we are interested in is what we call the Thom polynomial of this algebra A or AK is this locus of where the map has this singularity. So for this example, the Runge formula is the sigma f, 1f, where this is kind of really just the singularity locus is given by the top Chern class of the difference bundle. And then it turns out that this Thom polynomial actually can be represented as a tautological integral on the curve in the Hilbert scheme. So remember, this is not the main component. This is a component of the puncture Hilbert scheme. It's a small component which contains all fixed points. But this is actually this Thom polynomial can be interpreted as some tautological integral on this component. So I will not explain the explicit formula which can derive from this. Just the idea that actually the interpretation somehow important. Now there's a multi-point version of this. It's kind of studied by Kleiman and his school in the 1980s. So what is the multi-point? The multi-point version is the following. You take now this is in the target space. You take those points in the target space M, where the fiber has coordinately at least k, kind of, and that's the question again the same. What is this class which is represented by this locus? And it turns out that it's a bit more complicated formula, but it can be reduced to integration over the main component now of the Hilbert scheme of k points on Cn of some Euler class. So it's going to a tautological integral. The point is that I really just want you to see that these things actually appear directly in these applications, in these problems. So this is actually a highly non-trivial fact, and we can derive formally for this explicit residue formally. The third application I would like to mention before I turn to hyperbolicity is again an old. It's a old but not very well-known approach to curve counting due to Lothar Götzsche, which actually uses the question to tautological integral. So this is this classical question, enumerative geometry. For instance, this data nodal curve counting. So nodal curve counts. So if you take a surface, this is an example. If a surface and we fix the algebras to be this three-dimensional algebra, which is the square of the maximal ideal on C2, then this geometric subset is really sits in the Hilbert scheme of 3 S points. So you like 3 points at each point, and we have S of them, so you have 3 S points. And it turns out that if you have a sufficiently ample line bundle over S, then the number of S nodal curves in a generic subspace of this linear system is given by this tautological integral. So you take this geometric subset has dimension 2S. You take the top Chern class of the tautological bundle. This is a very nice and simple topological fact. But due to the fact that this is actually was unavailable, it's not very well known. But the point is that we can now reuse some formula, and then we can come up with some iterative residue formula for these counts, and then more generally for any kind of counts of curves with any given singularities. So the point on this slide is that we have these 3 problems all reduced to the same type of question. This kind of integrals over this compactification, if you like, of the jet moduli space. I think that was the message. Yeah? And here. So, yeah. Any questions? Yeah. Yeah, the first one. So, this one. Yeah, so you take, so how you give the polynomial in the end? Yeah, sure. Yeah, okay, so what happens is that, okay, roughly, the short answer is the following. So first of all, this is either a local object, which means that you have the curve in the Hilbert scheme was Cn. So you see, as we saw before, this is just this quotient of the jet moduli this diffeomorphism group. The thing is that there is this, it's kind of what happens if we use equivariant localization. So Cn has an action, a torus action, we use this. And when you apply equivariant localization, you turn it into residue, you get a polynomial in the weights of the action. And then you substitute the Chern roots of your manifold into those weights. Roughly, that's the story. That's kind of a general topological thing. So whenever you have such a thing, if you apply localization, then the weights correspond to the roots of the manifold. It's kind of this universality. And then the residue, what you get is kind of it's a polynomial in the weights for the action, and then you get is a symmetric polynomial in the Chern root, so you get what you want. Okay. So that's okay. Okay. So now we turn to the hyperbolicity. So that's kind of is kind of the second and the third compactification of this jet moduli space, which I'm focusing on now. So I will explain. So yeah, this is a very short introduction. Maybe this is a little bit not necessary. I'm sure it's not necessary here. So, but this is kind of a very classical exercise. You have a curve of genus at least 2, and then if and only if Lie holomorphic map is constant. And this is really the proof. It's just the idea is that this map will lift to the universal cover, which is a disk. So and it's bounded, so it's constant. And that's kind of it's a little bit stupid, but it's kind of, this is what I would like, just a very short introduction to say how to characterize surfaces or manifolds which do not have entire curves. So you see that this ampleness property plays a crucial role. And indeed, so it's kind of, I will not, there's a huge vast literature of this and history. I'll just really state the key definitions and conjectures. So complex manifold X is called broadly hyperbolic if there is no non-constant holomorphic map, and weakly hyperbolic if there is this kind of any curve which holomorphic, so any entire curve sits in some, there's an algebraic subvariety, a proper subvariety of X such that any entire curve sits in that. And so the Green-Griffiths line conjecture formulated in this way says that for every projective algebraic variety X of general type is weakly hyperbolic, and there is the Kobayashi conjecture says that the generic hypersurface now of degree d large enough is broadly hyperbolic, where this conjecture best bound is linear. So that's kind of the point, is that dn is 2n plus 1 or 2n. So these are the two main kind of hyperbolicity conjectures on the horizon, and I really want to talk a little bit about this in the second half of the talk. So I'm probably not the right person to give a very nice overview of the history of this problem, because this is a vast, huge history. But let me just mention that the strategy, which was worked out by Jean-Pierre Demailly and also in the 1980s, since the 1980s, and of course not just by them, but they are two key figures in this story. Is this kind of following two steps. So the first step is find the differential equations satisfied by jets of curves to prove algebraic degeneracy. So the first step is finding differential equations such that any entire curve must satisfy. The second step is find enough independent differential equations such that when all of them are satisfied, that the curve must be a point. A holomorphic map must be a point. So that's kind of the idea. It's a huge, rich literature, and there's mentioned some recent highlights. First, for very generic surface, there is a proof for with quite efficient degree bounds. And these are still the best known bounds as far as I understand for surfaces. So then there is a big breakthrough in 2009 when actually I joined this, when I first learned about this problem, and this is the point where I actually started working on this, is in 2009. So Simona, Gerald, and Evan actually, they came out this paper which proved the Green-Griffiths line conjecture with, for generic hypersurfaces with effective lower bounds on the degree. So this is an exponential bound, and this was definitely the first. And actually, also there's a strategy which they used was incorporation of the already known kind of strategy. Then, so on the Kobayashi side, there was a proof by Siu and then by Broadback in 2016. They proved the Kobayashi conjecture for sufficiently high degree. And then from the, actually we can work out some effective exponential bound on the degree from that. And then these two stories actually, GGL and Kobayashi, somehow they ultimately actually came together in 18, which is, I was here actually in Grenoble when Eric Reed gave this talk about this result. It's a super nice result saying that these two conjectures actually kind of one follows from the others, in the sense that if you have a degree bound for the GGL conjecture, then it gives automatically a lower bound for the Kobayashi conjecture. So so let me spell out a little bit this strategy a bit better. So the strategy is really about this jet bundle. So we have this jet bundle JKX, which I defined before. So this is the set of jets or to X of curves. There is this diff K action on that, which is the reparameterization action acting on fiberwise. And the idea is that we can take the algebraic differential operators are basically polynomial functions on this bundle. So if you take a local coordinates, then you can write any differential equation as a polynomial in the derivatives, right? With holomorphic coefficients. And the jet differentials bundle was first introduced by Green and Griffiths in '78, was this bundle of polynomial functions on JKX where they have this weighting. So there's a C-star action, so it kind of comes with a weighting, so it's a graded algebra. And then Demai later realized and introduced this invariant jet differentials bundle, where he actually incorporated into the story this diffeomorphism action, which means that he took actually differential operators which are invariant under this, this reparameterization group. Now, so what really happens is that what we would like to say actually is that this Demai jet differentials bundle is really, by the way, because it's that's what we want expect, is like invariant of polynomial functions on this bundle. So it's going to be polynomial functions on the quotient, right? So how to like, that's the intuitive picture, is that this Demai algebra is really the UK invariant part of the Green-Griffiths bundle. So it's going to be the UK invariant part of this polynomial function ring on JKX. So in other words, it contains, or in some nice, for some nice compactifications maybe, it is equal to the polynomial ring of functions on the quotient, right? So we can't expect this last thing to be equality unless we are very lucky and get some sort of nice compactification which capture all the invariants. But that happens quite rarely. But the point is, the whole point in this story, and that's kind of a very lucky situation, is that it's enough for us to have a containment. And that's why actually it's enough for us. And that's kind of, I'm going to show, that's actually what makes it really interesting, is that in some sense, for this strategy, any compactification of this quotient works. If you take a projective completion of this quotient, you can play the same game. You can check what's the what it gives you in terms of the degree. So let me explain this. So we want the fiber-wise projective completion of this jet bundle, which means that it's a projective completion. It comes with a, so you know, then the tautological bundle, so it's, it actually, the sections of the tautological bundle of this projective completion gives you invariants. And that's, as I said, it's a subset of, it's a subspace of the full invariant algebra of Desmaillet. So, and in particular, we can try to use, and that's what happened for many years, to use the Desmaillet sample tower to encode these invariants and work with these invariant jet differentials as a sections of some bundles over the Desmaillet sample tower. And that works very well. Actually, the Desmaillet tower captures more or less all the invariants. Whereas if you take another compactification, like a non-reductive jet, it doesn't capture all the invariants. It's some part of that. It's some graded subring of the graded ring of invariants. But that's enough, because any section of that still gives some invariants. And at the end of the day, what we want really is just to get one global section of such of that bundle. Anyway, so here on this slide, I collected the main and crucial ideas towards the hyperbolicity. So it's a beautiful, beautiful strategy and story, which I learned when I was in 2010. So we have this is the fundamental vanishing theorem due to Green-Griffiths origin only. Is that if you have a, so the idea is that if you have a polynomial, if you have a global section of a twisted bundle of the Desmaillet invariant jet differentials with an ample divisor, and then for any entire curve, any entire curve must satisfy that differential equation, right? So, and the point is that here we fix the order of k of the differential equation. So it means that we fix k, we fix the order of these jets. Now, it's just what it implies is that if you have a set of sections, then the image of this entire curve lies in this Green-Griffiths locus, which is just the intersection of the base loci. So the GGL, the Green-Griffiths conjecture holds if we find enough independent jet sections so that this is not the whole X, right? So that's kind of the goal. If the intersection of these base loci is strictly smaller than, or it's a subvariety of X, it's a closed subvariety anyway, and then we are done. So now that's again, the second part of the strategy is kind of difficult to summarize in 2 lines, but the idea is that is about how to construct these enough independent jet differentials or sections of this bundle. But that's actually what was worked out, and the ideas come from Clemenceau and Bozan, and then CU extended, and Merkel and Darundu. So Lyon and Darundu actually had a final version which makes this limit, bound limit, even a bit better. So the point is that we can find, the idea is we can find enough independent sections of this bundle, or enough independent differential equations, and that's using some sort of slanted vector field techniques, using the universal family. And defining from one section, we can define, using some derivation along the vector fields, you can define some new section. And it turns out that this is independent from the previous one, and you can go down. Anyway, so the point is that this strategy works out really, really nicely. And that's incorporated in the paper of Diverio, Merkel, and Russo in 2009 with this first explicit low degree bound in the Green-Griffiths conjecture. But what I really want to say is that what is the real result there is that if you have any So I really a little bit of reformulation of this result, because what I say here is that if you take a fiber-wise projective completion of this quotient, so for any with a canonical bundle OX, and if we can prove that there is a global section of this twisted bundle, which is twisted bundle is now twisted by this ample bundle Kx for some sufficiently high degree of the hypersurface or X, then the Green-Griffiths-Lang conjecture is true for generic hypersurfaces with this degree bound. So it's first you have to have such a bundle, but also there is this other numerical lower bound which comes from the fact that we have to shift. And that shifting cannot be very small because this data comes in the denominator. So we have to be very careful and with how we make this shift. So that's kind of the main part. So what we really want is the sections of this bundle. And the question is how to find sections of this bundle. And that's where actually this beautiful theory of Jean-Pierre actually comes in, which studies the holomorphic Morse inequities. But this is the algebraic version due to Trapani. So we have a holomorphic line bundle over X. And assume that we have this decomposition into two NAF bundles. Then it's always true that this is an inequality regarding the Betti numbers of these powers. So you have, in general, what the upshot is that if you prove that this intersection number is positive, it implies that this has a nice section, that there's a global section of this bundle for sufficiently high M. But we actually don't care about the value of M here. So that's actually really what the upshot is, that this strategy and this result reduces this problem to intersection theory. And that's kind of that's the only where I kind of could attach to this problem, and actually is really about intersection theory now on this moduli space, which is a quotient. Right. So that's kind of the strategy in a nutshell. And so as I mentioned, as I stated here, so we can take, in some sense, any fiber-wise compactification. So I tried the Curviner-Hilbert scheme. It didn't work out really well, also, although it gave result. But really the nice thing about this non-reductive GIT quotient that the intersection theory is nice. So this we can calculate this intersection number and prove the positivity of that. So let me just in the remaining 7 minutes, let me just quickly go through this construction. So as I mentioned before, and as the first slide, we had this group, this diffeomorphism group, which is a C-star extension of the unipotent radical with positive weights on the Lie algebra of U. And there's a linearized action of that on the affine space. But now the crucial step is that we introduce this Z min, which is just the minimal weight space for the C-star action on X. And this is X min is just the contracting set. This is the Bialystock-Birula stratum, such that points which where the limit, so if it's acting on by the C-star, the limit point sits in Z min. So it's a contracting set of Z min. Now, if you have this embedding into some projective space, so X is a projective variety, then it gives some sort of GM moment map, and we can define a U hat moment map from that, just roughly speaking, basically by projecting the moment map to the corresponding Lie algebra. And the point is that we constructed this non-reductive GIT quotient, which is a projective quotient, but has also a symplectic description. So I put down I think I will not go through the details, but the point is that I really follow the reductive picture. So there is this moment map, and the zero-level set of the moment map really serves as a slice for the maximal compact subgroup in X in U hat. And so this means that the non-reductive, yeah. So this is there's a diffeomorphism between the non-reductive GIT quotient and the symplectic quotient, and that actually allows you to introduce deduce some cohomology and intersection numbers and integration formula for the quotient, which is not really crucial now to explain, but it works very well. And that actually indicates that this non-reductive GIT quotient is really in some sense canonical, because this is really something which is very which is a fundamental fact about this GIT quotient, that they actually have a symplectic description as well. So we have, in particular, we have this integration formula in the end, is kind of a Jeffrey-Kirwan type integration on the quotient. So in other words, we can put down integration, we can put down intersection numbers integrations over the quotient of any bundle with a very efficient integral formula. It's going to be a residue formula. And then, so this actually, using this, we could, as I mentioned, the algebraic Morse inequalities give you this, reduces the problem to intersection theory. We use this formula to calculate this intersection number, so we can come up with a formula for the intersection number and prove the positivity with sufficiently high, in this case, polynomial degree of the hypersurface. So the result is that these both hyperbolicity conjectures are true for degree at least roughly n to the 4. So it's still not, it's far from being linear, which is the conjectured bound, but it's getting closer. Now there's a remark here, which is actually a super nice development from this year. So Benoit came up with the idea that actually this goes through, I mean, a slightly worse, but actually still a polynomial bound can be achieved by using not the quotient bundle, but the original Green-Griffiths bundle. Sorry, this is a EGGKM. So you can somehow go through this strategy using, instead of the quotient, you can actually use this. It gives slightly, it seems to give slightly worse, but still polynomial bound. I think maybe this difference is really from the factor of the quotient. In fact, the dimension of the group which we quotient by is n. And this is a sketch of the proof, which I will not, it's not very important. So we have the net composition, and really just this intersection number, which really appears also in the Diviero-Merkel-Rousseau paper, but now it's really on a different compactification, on this non-reductive GIT quotient. So that number really has this formula, this iterated residue form. I mean this full thing is kind of long, and then you still have to substitute this into there. But it's still manageable, so it's much more, the point is that it's manageable, and it's way simpler than integral formulae on the tower, on the Demailly tower. So I think I will stop now, and thank you very much for your attention.